In this module, we're going to discuss equilibrium in aqueous solution, in particular the equilibrium concerning the dissolution of a salt which is only slightly soluble. So examples of the type that we are going to be discussing are the case of ionic solids, for example, calcium sulfate, that put in contact in water, they dissolve into it, but they dissolve into the ions. In this case, calcium 2 plus cations and sulfate anions. And the solubility of this salt is relatively small, limited. In this case is 0.4 or so grams per liter. Only 0.4 grams of the calcium sulfate dissolves into 1 liter of water. Another example is lead iodide, that when it is put in contact with water, it dissolves into lead cations, lead 2, and 2 iodide anions. In this case, the solubility at 25 degrees centigrade is 0.5 or so grams per liter. Another example is the case of silver chromate that dissolves into silver cations, 2 of them, and chromate anions. The solubility in this case is considerably smaller. An order of magnitude is 0.02 or so grams per liter. And for another example, silver iodide that dissolves into silver cations and iodide anions, and the solubility is considerably smaller. Now is about 2 times 10 to the minus 6 grams per liter. That is only about 2 micrograms of silver iodide solid dissolved in a liter of water at 25 degrees centigrade. So all of these cases that we have seen can be summarized in this dissolution equation. Notice that this dissolution equation takes into account that there might, in the formula for the ionic solid, we might have more than one cation or more than one anion, and that is indicated with these subscripts X and Y. So when this solid dissolves, it contributes X cations that have charge N plus and Y anions, and the anions B have charge N minus. N plus and N minus are small natural numbers, for example 2 or 1 or so. So notice that the number of cations times the charge number of cations plus the number of anions producing this solution times the charge number of the anion, they have to add up to 0 because the ionic solid is electrically neutral. It does not have net charge. So we have to produce as many cations with charge number N plus and as many anions with charge number N minus, so that these sums add up to 0. And as you can see from these formulas, these chemical formulas, it's relatively simple to achieve that. So here is the general dissolution equation for an ionic solid of this type. And now let's consider the equilibrium of this solution, in particularly in water. That's what we're going to discuss. So the equilibrium constant expression for this dissolution takes this form. First of all, the equilibrium constant usually has associated a subscript Sp for solubility product, and it's referred to as the solubility product or solubility product equilibrium constant. Um, so in this reaction in the products we have the ions. So in this case we have the cations A and plus, and they will be expressed to or powered to the stoichiometric coefficient X, and the concentration of the anions B and minus, powered in this case with the stoichiometric coefficient of the anions Y. Notice that the reactant in this case is a solid, and the solid does not enter in the equilibrium constant expression. So the equilibrium constant expression for a dissolution reaction of this type takes this simple form, and let's consider some examples. In the case of calcium sulfate that dissociates into one calcium and one sulfate, then the equilibrium constant expression is the solubility product for calcium sulfate is the concentration of calcium 2 cations times the concentration of sulfate anions. Notice that both stoichiometric coefficients are 1, so the powers are 1. In the case of lead iodide that dissolves into lead cations and 2 iodide anions, the solubility product for lead iodide is the concentration of lead to power 1 because the stoichiometric coefficient is 1, and iodide to power 2. At 25 degrees centigrade in water, these solubility products have these values that I wrote here. In the case of calcium sulfate, it's about 9 times 10 to the minus 6. And in the case of lead iodide, 7 times 10 to the minus 9. So these reactions are very much reactant favors. They do not dissolve very much. These salts are very sparingly soluble. Other examples that we saw before, silver chromate. In this case, the solubility product has a value of 10 to the minus 12 or so, and the equilibrium constant expression involves the concentration of silver to power 2 because the stoichiometric coefficient is 2, and chromate to power 1. Last example, silver iodide. The solubility product at 25 degrees centigrade in water is about 10 to the minus 16, very slightly soluble. And this is the equilibrium constant expression involving cations and anions, 2 powers 1 because the stoichiometric coefficients are 1. Okay, so now that we have seen or introduced the dissolution reaction of an ionic solid in water, and the solid is only sparingly soluble, and the equilibrium constant expression, let's begin to do equilibrium calculations. So what can we do knowing a solubility product and an equilibrium constant expression? Well, the first thing we have to get used to is how to write rise tables for these dissolution equilibria, and let's consider as an example barium sulfate. It has an ionic product of 10 to the minus 10 or so, and on dissolution barium sulfate dissolves into the cations barium 2 plus and sulfate anions, one of them each. So initially we put the solid in contact with water, and we do not let the reaction, it's a conceptual process, we do not let the reaction or the dissolution take place. So initially we just have solid in contact with water, but in the solution the concentrations of barium and sulfate are 0. What we are writing here are concentrations in moles per liter. Then we let the dissolution take place and we wait until equilibrium is reached. Notice that some of the solid will dissolve, and therefore we have a smaller amount of solid present in contact with now the solution. Notice that per mole of barium sulfate that dissolves, 1 mole of barium dissolves, is produced, and 1 mole of sulfate anions are produced. So if S moles per liter, and S is the solubility of the salt expressed in moles per liter, if S moles per liter of barium sulfate dissolves, S moles per liter of barium cations are produced, and S moles per liter of sulfate anions are produced. In this case, things are very simple because the stoichiometric coefficients are 1. Later we're going to complicate. So the solubility, uh, the equilibrium constant expression is the ionic product for barium sulfate, which is the concentration of barium times sulfate at equilibrium. Notice the powers are 1 because the stoichiometric coefficients are 1. So we read from the equilibrium line in the rise table that at equilibrium the concentration of barium is S, and at equilibrium the concentration of sulfate is S. So the ionic product K is S multiplied by S squared. So from an expression like this, we can calculate the solubility of barium sulfate at equilibrium if we know the solubility, the ionic product. So from this equation, we see that K is equal to S squared. We can take the square root on both sides to find S. The solubility is the square root of the ionic product, in this case the square root of more or less 10 to the minus 10, and the square root of 10 to the minus 10 is very close to 10 to the minus 5, and solubility is expressed in moles per liter. So the solubility of barium sulfate in water is quite small. This ionic product, 10 to the minus 10, means that the concentration of barium cations and sulfate anions equals the solubility is basically 10 to the minus 5 moles per liter. Notice that these concentrations, I'm reading them, it's S at equilibrium from the rise table. Okay, so let's consider an example, the determination of the solubility product from if we know the molar solubility of a salt. So consider this problem. What is the solubility product of silver iodide in water at 25 degrees centigrade if we know that the solubility of silver iodide is 3 times 10 to the minus 7 moles per liter? So we construct a rise table for silver iodide, and what we want to know is what's the solubility product. So initially we have solid in contact with water and none of the dissolution process has occurred, so the concentration of the ions produced in the dissolutions is 0. Now we let the dissolution take place and wait until equilibrium is reached. So some of the solid has dissolved, the amount of solid in contact with the solution has decreased. And notice that per mole of silver iodide that dissolves, a mole of silver cations is produced, and a mole of iodide anions are produced. So if S moles per liter of silver iodide dissolves, S moles per liter of silver and S moles per liter of iodide are produced. So as before, the solubility product in this case is the concentration of silver cations to power 1 times iodide anions to power 1. because the stoichiometric coefficients are ones. These concentrations at equilibrium, we read them from the equilibrium line. Each of them is a solubility, and the product is solubility squared. But notice that in this case the problem is the reverse of what we saw before. In this case the data is the solubility S, and we want to know what's the solubility product. So the solubility from the data is about 4 times 10 to the minus 7 moles per liter, and that square gives about 10 to the minus 13. And 10 to the minus 13 is the the solubility product of silver iodide. So this, it's not written, but it's done at 25 degrees centigrade. So the solubility product of silver iodide in water at 25 degrees centigrade turns out to be 1.5 times 10 to the minus 13. So far we have been discussing a simple case where the solid, when it dissolves, produces only one. The stoichiometric coefficients are one for the cations and one for the anions. Let's complicate and consider the general case. A solid that when it dissolves gives X cations and Y anions. X and Y are the stoichiometric coefficients. So initially we put the solid in water and we don't let the dissolution take place. So we just have solid in contact with water, and the concentration of the ions producing the dissolution is zero because we are in the initial state, the reaction hasn't started. Now we let the dissolution process take place and wait until equilibrium is reached. So some of the solid will dissolve, so we will have a smaller amount of solid in contact with the solution. Now, if you look at the reaction, per mole of solid that dissolves, X moles of cations are produced and Y mole of anions are produced. So if S moles per liter, the solubility, if S moles per liter of solid are dissolved, X multiplied by the solubility is the concentration of cations in the solution, and Y multiplied by the solubility is the concentration of anions in the solution. Remember, in this table we're using molar concentrations. That's because per unit formula of solid that dissolves, we are producing X cations and Y anions. Now the procedure is the same algebra before, maybe a little bit more complex. So the solubility product, as usually, is the concentration of cations to power X, because the stoichiometric coefficient is X, times the concentration of anions to power Y, because the stoichiometric coefficient is Y. Now these concentrations are the concentrations at equilibrium, which we read from the equilibrium line of the Rice diagram. So the concentration of cations at equilibrium is XS. However, this has to be powered by X because that's the power in the solubility product expression. The concentration of B at equilibrium is YS in parentheses, and we have to power Y. So now proceeding algebraically, this is the same as X to the power X, Y to the power Y, and S to the X times S to the Y, which is S to the power X plus Y. In most common cases, we will know the solubility product, and what we want to determine is the solubility. So we have to solve this equation for S. Well, the first thing we can do is pass these stoichiometric coefficients powered, dividing to the other side, dividing by the other side, and then take the X plus Y root. So S is the X plus Y root of the ratio of the solubility product. divided by these stoichiometric coefficients with the respective powers. Notice that an x plus y root is the same as powering what's inside the root to the power 1 over x plus y. This is a little bit abstract, so let us consider an example, and we'll see that it's very simple. So let's assume that we know what's the solubility product and we want to determine the solubility. So the salt in this case is strontium fluoride. And the question is, what is its molar solubility in water at 25 degrees centigrade? If we know that in those conditions the solubility product is about 10 to the minus 5. So as before, we construct a rise table. Strontium fluoride dissolves into strontium cations and 2 fluoride anions. And as the problem says, the solubility product is 10 to the minus 5. So initially we have solid in contact with water. There are no ions present because the dissolution has not started. We let then the reaction proceed towards equilibrium, and when that happens, some amount of solid has been produced. Notice that per mole of strontium fluoride that are dissolved, we produce 1 mole of strontiums but 2 moles of fluoride. So if S moles per liter, the solubility of strontium fluoride are dissolved, we produce S mole of strontium cations, but twice that amount of fluoride anions. So the equilibrium constant expression is the solubility product of strontium fluoride equal to the equilibrium concentrations of strontium to power 1 because the stoichiometric coefficient is 1 times fluoride to power 2 because the stoichiometric coefficient is 2. These are equilibrium concentrations that we read from the equilibrium line. S for strontium to power 1 and 2s is the concentration of fluoride, twice the solubility, to power 2 because the stoichiometric coefficient is 2. Okay, but 2 squared is number 4, and s multiplied by s squared is s to power 3. So to solve for s, we pass the 4 dividing to the other side, and then we take the cubic root. So S is the ratio of the ionic solubility product divided by 4, all to the power 1/3. The solubility product was 10 to the minus 5 or so, divided by 4 and to power 1/3. We find that the molar solubility of strontium fluoride in water at 25 degrees centigrade is 1.6 times 10 to the minus 2 moles per liter. Okay, so far we have at the very beginning talked about solubilities of ionic solids expressed in grams per liter. And then when we did the rise table, we used solubilities expressed in moles per liter. Notice that the relation between the two is very simple. We just have to multiply the molar solubility by the molar mass of the salt in order to get the solubility of the salt expressed in grams per liter. So, for example, we at some point during the slides or the discussion, we calculated that the molar solubility of barium sulfate is about 10 to the minus 5 moles per liter. The molar mass of barium sulfate is 233 or so grams per mole. Multiplying these two numbers, we find that only 2.4 or so grams of barium sulfate dissolve in water at 25 degrees centigrade. With this, we conclude the discussion of solubility of sparingly soluble salts in water at 25 degrees centigrade. And one important thing that we have discussed all throughout is the case that the solid dissolves into pure water. In following discussions, we need to address what happens when the solid dissolves in more complex media, like for example solids that already have salts present. Other salts dissolved present. Thank you very much for listening.